So exponential functions are going to look different than a lot of the functions we've worked with in the past. If I give you, I did, thank you. You don't need to write this down. This is just me drawing on your prior knowledge so that you can relate what we're doing today. But I just want you to see this. If I give you this equation, and I said graph it, do you know what your graph would look like? Y equals 2x plus 4.
Plus 4.
You'd go up 4, and then you'd go up 2 over 1, up 2 over 1. What does the graph appear to be then? Is it a circle? No, what is it? It's a straight line. Okay, so this is a linear function, right? We've talked a lot about linear functions, what we do with that. We're moving into exponential functions, and exponential functions will never be a straight line. They cannot be a straight line. Have you ever heard someone say they're growing exponentially? Yeah. Okay, what that means is it was a slow go, and then all of a sudden they shot up, right? So growing exponentially, exponential growth, exponential decay. Have you ever heard of exponential decay? It goes slow and then drops. Okay, well, for you guys, it's this way, typically. So that's what we're going to be looking at in this next couple of sections, is exponential growth and exponential decay and their functions and how it works. So this is going to be a function in the form of y equals a times b to the x power. Notice my x is not the thing that comes after m in like the y equals mx plus b format. Okay, now your x, your variable that we're going to be working with, is an exponent. We've done a lot with exponents lately, haven't we? Yes, Khalees.
Is this
Confusing? You're going to have to let me know after you hear the lesson. I don't think so, but you'll have to be the judge of that. So here's the scenario. A cannot be 0 because if A is 0, then everything is 0. There's no function left. B is going to be a number greater than 0 because we're going to be talking about growth. And if something has a growth of 0, it's not growing at all. So B can't be a 0. And B can't be 1. Okay, now here's a question for you. If B is what we're growing by, and I make B 1, what happens when you multiply something by 1? It stays the same. 1, what I need you to do is I need you to think of that number kind of like a percent. If I say the growth factor is 1, all that's saying it is 100% of what it started as. Did that grow? But if I say it's 1.01, that grew. It's bigger than the 100% that it started as. So the number cannot be 1. It needs to be a number greater than 0. If it's a number greater than 0 but less than 1, it's a fraction. What do you suppose happens to it if it's between 0 and 1? If 1 is 100% and I say it's a half, what happened to it? It decreased, right? It's shrinking. So exponential growth, exponential decay is what we're going to get into with this. So here's just a couple pictures to show you what this looks like. Y equals 2 to the x is going to be this red graph, which I'm now making pink. Y equals negative 2 to the x is going down. Whereas this one, now it's a fraction out in front, and that is decreasing but above the axis. This is a negative 1/2 out in front, which is actually increasing this way, but below the axis, okay? So that just kind of gives you a visual of where things get impacted and how they are impacted. Okay, we're going to take this down to like the bare basics here. If you have a table, okay, all of your x values have a common difference. What's a common difference? What? Did you say something, Ava? Oh, I thought you said something. A common number that you are doing what? Not multiplying, dividing. What's a difference? If I find the difference between 10 and 6, I subtract, okay? So a common difference is addition and subtraction. If you're adding and subtracting by the same amount, it's a common difference. So what they're saying is if your x values are changing by the same amount, okay? So look here, 0, 1, 2, 3. They're going up by 1 each time. If that happens and all of your y values have a common difference as well, so they go up by the same amount, this one doesn't, spoiler alert. If they're changing by the same amount in addition or subtraction, then that table represents a linear function. When you graphed it, you would get a straight line. Okay, what we're going to do today is your y values will have a common ratio instead. Do you remember, what was the formula we used that had a common difference? Did we do the arithmetic series? A sub n equals a sub 1 plus n minus 1 times d. We did that, right? Yes. This one? Okay, that had a common difference. We were changing by the same amount, okay, with addition and subtraction. This one is saying if your y values have a common ratio, so common difference, here, maybe you want to write this in. Common difference is addition and subtraction. Common ratio is multiplication and division instead. When that happens, when the thing that you're changing your y values by is involving multiplication and division, then it's an exponential function. And that's what we're going to focus on today, is the exponentials. Now, you're going to see some linears because I want you to differentiate between the two. But we are focusing more on the exponential. Sydney. Yeah, leave your phone up here. Okay, so here's the setup. Look at your table of values. Are you changing with addition and subtraction by the same amount each time? On the top you are, plus 1, plus 1, plus 1. Are you able to add the same thing here each time? No, this is plus a negative 2, plus a negative 6, plus a negative, right? The number keeps changing. What doesn't change is if we do what with it? If we multiply it by 3. If I go times 3, I get this. If I go times 3, I get negative 9. If I go times 3, I get negative 27. What they're saying is, as long as this is going up by the same amount with addition, and then this one is changing by the same amount with multiplication or division, this is exponential, okay? So does this represent linear or exponential? This one would be exponential. Do you know what this graph would look like? Y equals 3x. It's a straight line. If you know that already, if you see slope-intercept form and you're like, I know that's linear, you don't need to make a table. If you want to make a table, you can make a table. But I look at this and I just go, that's a line. That's y equals mx plus b. Okay? So that's going to be a linear function. If you don't see that, here's what you could do. Plug in numbers for x and see what you get for y. If I plug in a 1, 3 times 1 is 3. 3 times 2 is 6. 3 times 3 is 9. Compare those. This is going up by 1. What is this doing? It's adding 3. If you can add the same thing all the way through, it's linear. Okay? If you multiply, it's exponential. So look at these next two and talk to your neighbor and decide, is it linear or exponential for C and for D? Linear or exponential? I forgot to start recording again. Okay, population growth says this. Stick with me. Suppose 30 flower beetles are left undisturbed in a warehouse bin. This is gross. The beetle population doubles each week. Here's the function for that. Okay, so you don't have to come up with the function yourself. This is telling you. But do you see where it makes sense that it doubles in the function? What's the thing in the function that tells us that? It's the 2. This is your growth factor. We're doubling, okay? But you don't have to come up with it. I just want you to understand where that's coming from. This gives the population after X weeks. The question is, how many beetles were there after 56 days? If X is in weeks, then we have to plug a number in of weeks. But we have days. How do you make 56 days into weeks? Divide by 7. 56 divided by 7 is 8. So this is going to be your X. And then we're just going to plug that into the function. So get your calculator out, because I don't expect you to do this in your head. You're going to say f of 8 equals 30 times 2 to the 8th power. Plug that in, because I would hate for this to be the reason you do something wrong. This should be the easy part. Yeah. F of X is Y. Right? This is your X. Here. Right? This is X. This is saying when I plug that X value into my function, which is saying what does Y equals. You could write this Y equals 30 times 2 to the X. It's just f of X function tells us what we're plugging in to get the thing we're going to get, to get our Y. So it's just a different notation, but you can always swap f of X for Y and it will mean the same thing. What'd you get?
7,680.
7,680 what?
Days. Weeks.
Beetles. 7,680 beetles. If you plugged it in and you didn't get that, we should chat, because this should be easy. This should be just plug it into your calculator. So if you don't know how to plug it into your calculator, let me show you, okay? You just plug this into your calculator. We found 8 for your number of days, or number of weeks. So you plug it in. We're going to do it again, right here. Don't go blow your nose this time. Okay, the next one says this. An initial population of 20 rabbits triples, see the 3? Triples every half year. Sorry, we're delayed. The function, f of x equals 20 times 3 to the x, gives the population after x half-year periods. What are you doing right now? He's watching you. You playing a game? Stop playing games. You just changed your screen. I saw it light up different. Don't even. I'm not a fool. I've been doing this a while. Anyway, if it's x's half-year periods, and this is after 3 years, what are we going to plug in for x?
3.
Not 3.
6.
6. 3 years is 6 half years. Does that make sense? 3 years is 6 half years. Okay? So we're going to plug in a 6 for our x. Do you understand that? Okay. So if we say f of 6 equals 20 times 3 to the 6th, because that's your x, plug that into your calculator and tell me what you get. After 6 half years, which is after 3 years, you should have how many rabbits? How many rabbits? 14,580. Is that what you got? Should be what you got. Okay, so just be careful with what they're telling you x represents and if they change what they're talking about. If it's years when it's supposed to be half years, then you got to double it to hit all the half years. Okay? Questions? Okay. Then graphing. When you graph an exponential function, typically with these, knock it off. Do math with me. So here's your function. Y equals 3 times 2 to the x power. When we graph these, it's good to have negatives, it's good to have a 0, and it's good to have positives. So your typical, what you're going to plug in is -2, -1, 0, 1, and 2. Okay? The rest of this should be fairly simple, other than there's fractions that often show up, and if you struggle with the negative exponent, which we just learned how to do, then it could be a struggle. But your calculator will also help you a lot too. So this one says 3 times 2 to the x power. So you're going 3 times 2 to the negative second power. What is 2 to the negative second power? 1/4, not -4, right? Flip it over, 1/4. So this is, I'm going to write it over here. 3 times 1/4 is 3/4. So the point, the xy that you get is -2 and then 3/4. Okay, now here's what I want you to do. Plug into your calculator right now. 3 times 2 to the negative second power. 3 times 2 to the negative second. What did you get? 0.75. Hit your PRB, second PRB, and it's going to turn it into what? 3/4. Okay? So you can always plug it into your calculator and check it. Turn it into the fraction, you get 3/4. Okay, so this one, 3 times 2 to the negative first. What is 2 to the negative first power? It's not -2. 1/2. Oh, 1/2. Flip it over and make it a positive. 1/2 is 1/2. So this is 3 times 1/2. So that's going to be, your x value was -1. Your y value, 3 times 1/2 is 3/2, or 1.5, if you will. Okay. Plug in a 0. 3 times 2 to the 0 power. What is 2 to the 0? 1. What's 1 times 3? 3. Where a lot of people struggle. Will you put those away? Will you put those away? Where a lot of people struggle here is they try to multiply 3 times 2 first and then take it to the 0. You got to do the power first and then multiply by 3. So 3 times 1 is 3. So you get the point 0.03. Then plug in 1. 3 times 2 to the first is 3 times 2, which is 1/6. Khalees.
Wait, so non-negative exponents are like this?
No, we got rid of the negative exponent. Right? We turned it into 3/4 instead of 3 times 2 to the negative second.
Well, I mean, but it's still negative.
Right, but that's what we're solving. We're solving 3 times 2 to the negative second, which is 3 times 1/4. Right? So I did this to get me 3/4. So you're going to plug it in as a -2, but then solve, which is going to get rid of your negative. Yeah. Okay, last one. 3 times 2 squared. 2 squared is 4, times 3 is 12. Okay, so look at this. You get 5 points. Plot them. These 5 right here. -2, 3/4 is right here. -1, 3/2, that's 1.5. That's right there. 0.3 is here. 1/6. See how it's turning a sharper corner now? And then 2/12. Okay, your graph looks like this. And there's something with these called an asymptote. Have you ever heard of an asymptote? It's a funny word. An asymptote. Sounds like a bad word, right? It's the line that you'll always be approaching, but you'll never actually hit. So you will never actually hit the x-axis when you graph this, because there's an asymptote there. We're not going to do much with asymptotes, but asymptote. Asymptote. Only one S. It is a weird word. You'll learn more about it in Algebra 2. Okay, letter B. So this is the same setup. I'm actually not even going to do this one with you right now. If you want to do this one, great. You'll plug in -2, -1, 0, 1, and 2. So you're going to drop that number in for all of these. Just so you're clear, if you do this one right now, you get your y value is 1/18, your other one 1/6, 1/2, 3/2, and 9/2. So if you want to do this, this is what you should get. Okay, just make sure you're getting that when you calculate this. I'm not going to do it with you. It ends up being a curve that looks sharper than that. No, still not good. Not even going to graph it. But you'll get essentially that same curve that you got on this one. Okay, we're going to keep moving because this is going to do the same thing. Okay, so these last two are real world problems with this. And here's how this works, okay? It says computer mapping software allows you to zoom in on an area to view it in more detail. The function given here models the percent of the original area the map shows after zooming in X number of times. So they give you this and then they say graph it. Use your calculator, okay? Your calculator will be your friend here. You're gonna go 100 times 0.25 to the 0 power. Why do you suppose they're not using negatives here? You're not going to zoom in a negative number of times. Real world problems rarely use the negatives. Usually they start those at 0. So that's why this one doesn't have -1, -2 with it. Because in reality, you're not going to zoom in a negative number of times. You're going to zoom in 0 times or 1 time or 2 times. So here's your setup. If you plug that in, you get the point 0. What? What's 0.25 to the 0 power? It's 100. Yeah, that's 1 times 100 is 100. Okay, then you go here. 100 times 0.25 to the first power. So 100 times 0.25, and you get 25. Okay, then you plug in a 2. I'm not going to keep writing that out. Is that okay? You're just plugging it into your calculator, right? 100 times 0.25. Do you remember how to get that again? Second enter brings that thing up, and then you can just edit. You don't have to type it all in every time. If you don't know what I'm talking about, ask me and I'll show you. So if you plug in a 2, what do you get? Did you get 6.25? That's what I got. If you plug in a 3, you get 1.5625. And if you plug in a 4, you get a very small number, 0.39. I'm just going to round it. It goes 39020625. Okay, so here's the deal. If you have to graph this, you have a very broad range of numbers. What would you count by on your x-axis? Look at your x numbers. What are you going to count by there? Count by ones. 1, 2, 3, 4. So here's 0, here's 1, here's 2, here's 3, here's 4. It does not make sense to count by ones on your y-axis. You don't have to count by the same thing as your neighbor, as long as you make it make sense and you count by the same amount every time. So don't just jump up to whatever number you want, okay? This goes as low as 0.39 and as high as 100. What do you want to count by?
50?
So if you count by 50, you only have 2 hash marks that you need. You could count by 25, 25, 50, 75, 100. You could count by 10s. You could count by 15. Any of those are fine. I'm going to count by 10s, but you don't have to. You can count by something else if you want. What matters is that you evenly space them. So I'm going to go 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay, so now if we plot, you have 0, 100. That's going to go here. 0, 100. Okay, then you have 125. This drops big. 125 is right here. Okay, notice then it's more gradual. 3, 1.5, not quite as drastic. And then 4 is nearly touching the line. Your curve looks like this. Okay, your asymptote is the x-axis, so it's never going to go under that x-axis. You're not going to have negatives there, but that will be your curve. Questions on that? Okay, here's what I want you to see. This number was a decimal, was a number less than 1, and that is going down. Look at this one. This number, your growth factor, your B, is 4. Do you think this goes up or down? This is going to go up, okay? So if you plug this one in, if you plug in a 0, this is 100 times 4 to the 0 power. What do you get? 100. Same thing as the last one. Then plug in a 1. 100 times 4 to the first power. What do you get? You get 400. We're going up now. Plug in a 2. You get, 2. You get 1,600. Plug in a 3. 6,400. It's exponential. You're trying to make it linear. Plug in a 4, and you have 25,600. Okay, so this one, you've got some big numbers. What are you going to count by on your x's? Count by ones. Okay, what are you going to count by on your y's? 1,000. If you count by 1,000, you have to do 25 hash marks to get that last one in there. Here's the other option. If the one is like so far off, and you skip the last one because it just doesn't fit nicely, that's not the end of the world. But I would love it if you would fit all the points, because you do see a better version of it if you have them all. So, what do you want to count by? 5,000? Okay, so if we count by 5,000, 10, 15, 20, 25. All right, so plot these. 0, 100 is hardly above the line. That would be here. Okay, 1, 400, again, hardly above the line. To get up to 5,000 for that first hash mark, you barely moved up. 2, 1,600, still not even halfway up to the 5,000. 3, 6,400. Now we're finally above that 5,000 mark. And then 4, 25,600 shoots way up here. So exponential, that's really not straight, sorry. Exponential growth.